So here we're going to discuss the concept of electronegativity. Electronegativity is always in the context of a covalent bond, and it is defined as an atom's relative attraction for the electrons that are shared in a covalent bond. Another way to kind of think about it is that it is kind of like the greed that an atom would have for the electron density that it's sharing in the bond. The more electronegative the element, the greater its attraction for the electron pair. So electronegativity values vary by element, and there's a nice periodic trend. So in general, if you look at the periodic table, as you go from lithium all the way on the left side of the periodic table to fluorine on the right side of the periodic table, electronegativity is going to increase. So across a row on the periodic table, the trend is that electronegativity is going to increase. And that is similar to the periodic trends that we discussed in the previous chapter. You have effective nuclear charge increasing as you go across a row, and that means that an atom's relative attraction for electrons is going to increase across a row on the periodic table. Now, as we go down a column, say from lithium to cesium, electronegativity is going to decrease. So down a given column, you can generally say that electronegativity decreases. And you could say that for most any column, down a column in the periodic table. So electronegativity increases across a row and decreases down a column. And again, it's because of effective nuclear charge. So there are actual numerical values for electronegativity that differ by the elements, and they vary on a scale they vary up to a value of 4. They're kind of arbitrarily assigned values. So somewhere in the region of 0 to 4, you have the Pauling electronegativity values. Fluorine is the most electronegative element on the periodic table. Notice I'm not including the noble gases here because noble gases don't form covalent bonds. So we're stopping with the halogens. So fluorine has a Pauling value of 4.0. It's the most electronegative element on the periodic table. To give you some idea, lithium has a value of 1.0 for its numerical electronegativity. Cesium has a value of 0.7. So you can see how electronegativity decreases down a column and increases across a row just looking at these values. And these values are something you can look up. You can find them in your book if you would like. You don't have to memorize them. They're in figure 3-4 of your book. These are Pauling electronegativity values. But you can just use the periodic trends when you don't have those values handy to predict relative difference in electronegativity between two bonded atoms. So when two bonded atoms have different electronegativity values, so when two bonded atoms have different electronegativities, this creates a partial positive or negative charge on each of the atoms. And we call that a polar bond. So a polar bond means that each atom in the bond has a partial positive or negative charge. Now, the more electronegative atom is going to have a partial negative charge, and the less electronegative atom will have a partial positive charge. For example, let's take a situation where H is bonded to F in a covalent bond. Fluorine is the most electronegative atom in the periodic table. And we denote partial charges with the lowercase Greek letter delta, and then a superscript indicating whether the partial charge is positive or negative. So hydrogen gets a partial positive charge, and fluorine gets a partial negative charge. The more electronegative element gets the partial negative charge. So since fluorine is more electronegative, it gets the partial negative charge. Another way that this is represented is by drawing what's called a dipole moment arrow. So here I drew a dipole moment, and that's a special arrow with a little cross on its tail. The cross kind of looks like a positive sign, as you can see there. So that cross goes towards the more electropositive element. The dipole moment arrow always points towards the more electronegative element. So you can either use these little partial charges or the dipole moment arrow to indicate electronegativity in a bond. Now, what's happening here in the bond is that fluorine is so electronegative, it's so greedy and hungry for the electrons in that shared bond that it pulls the electron density in the bond towards itself. So you get an unequal charge distribution. You can draw a cartoon of that. Here's H and here's F. And my electron density is going to be huge around F, but relatively minuscule around H. So this is kind of an electron density distribution cartoon. It's very unequal because fluorine is busy pulling all of the electron density towards itself. It's very greedy for electron density.